-1. Hi, welcome back to Math 234. I am still your host, Steve Dragoo. Today we are going to finish up the practice exam. So last time we covered the last 4 problems of the practice exam. Today we're going to go back over the first 5 because I felt like they grouped well in that order since the last 4 directly tied into the stuff we had just been doing. So those last 4 problems really come straight out of the chapter 16 material, the different integration theorems we had. The first half of the practice exam we're doing now is a review of everything else from the semester that I think you should put some eyes on. So with that in mind, I do also want to point out a couple of other things in my notes. If you look over onto the left bar of the screen, I think I've pointed these out before, just in case I hadn't or you'd missed them. There are lots of tabs, including some with exam reviews from previous semesters. Also, I put the formula sheet over here because, you've got access to the formula sheet on D2L, but in case you needed it directly from the notes, here's a copy of it. I've also got each of the old reviews we did broken down by exam, including one that is specifically for the post-exam 3 stuff. That I did our practice exam instead of doing this, but there are plenty more problems here, including a whole bunch of web work problems. If you're still working on those before the end of the semester, go take a look at those. Speaking of web work problems, there's another tab that's previous homework, all sorted by the homework number. So if you're, again, trying to finish up a bunch of those homework problems right at the end, I've worked out a few of them. These are the ones I get just the most questions about. Speaking of the homework, there should have been an announcement on D2L that talked about the last day to use your web work achievement items. You have those because the set or the web work itself will stay open until like the end of finals week. But we need to pull grades much earlier than that. So the last sets are due Sunday nights, and then you've got all of Monday to use any of your leftover achievement items. So if you want to use any of those before the semester's done, make sure you use them by Monday night. And I do mean anytime Monday night. I'm going to pull grades Tuesday morning or Tuesday afternoon because I imagine I'm going to be up late Monday. So I'm going to sleep in. So Tuesday afternoon-ish. I'll pull grades. Make sure you use your achievement items by then. Also, the weekly reviews are a pretty good spot to go review material. I have all of the weeks with their worked out solutions posted in my notes as well. So if you haven't been looking at those, it might not be a bad idea to take a peek at them. All right, and with all of that said, now let's return to the practice exam, including looking at our formula sheets, because it's got a bunch of good stuff on here. Maybe I want to just highlight a couple of things. Let's see. It's got equation of a plane on here. We'll be using that today, so I'll just highlight it. So I know we're going to want it. What else is of particular interest over here? The second derivative test. I'm going to call back to that one when we need it, but we're going to use it today. So that's on the formula sheets. Also, the Jacobians for cylindrical and spherical coordinates are on here, though they're a little bit hidden because I don't just straight up tell you dv equals the Jacobian part. Instead, they are baked into the definition for those triple integrals. All right, but the Jacobian is listed on the formula sheet, and you might end up needing those when you tackle this stuff. Definition of conservative is also on here. So remember that definition of conservative applies if you're going to use the fundamental theorem for line integrals, because we need to make sure that our field f is the result of the gradient of some function. Right, so gradient f needs to be equal to the field. And then also Green, Stokes, and the divergence theorem are on there too. And we basically know we'll be seeing one of each of those questions. So those are all on the formula sheet. Make sure you kind of know where to find them. Oh, and also, I suppose I want to point out area and volume equations. particularly since we used those a lot when we were evaluating the integrals on Wednesday. Like, so a whole bunch of the integrals that we did just worked down to like the double integral of dA or the triple integral of dV. And then we can solve those just by calculating an area or a volume instead of needing to completely do an integral. But all right, enough of my soapbox. We're here for the practice exam. So let's get it. Number one, we want to find the equation of a plane which contains the line R, given right there, and the point 0, 0, 1. So, concept, or conceptually, real quick, the thing that we want. To find the equation of a plane, we need two elements. We need a normal vector, and we need a point. Any point in the plane will do, but we have to find a normal vector to go along with it. We already have a point, 0, 0, 1. It's given to us. And really, we have 2 points because we've also got 2, 3, 1, because that's a point that's in the line. We know that entire line needs to be in the plane. But more on that in a second. So we've got our point. Now we just need a normal vector. And the easiest way to get a normal vector is either to take the gradient of some function or take the cross product of two vectors that lie in that plane. Any two vectors will do. So step one is sussing out two vectors from the given information. So I'm going to rewrite that line so that it looks a little bit more usable to us. So R of t is the vector 3, 2, 1. 3, 2, 1 times t plus the point 2, 3, 1. 2, 3, 1. Where I'm pulling vector 2, 3, 1 to get that vector times t. So I've got a direction vector for the line, just based on the coefficients for t. And on the other side, this 2, 3, 1 creates the other point that's on the line. But with those parts complete, what do I have? I split my line apart into a direction vector, which needs to lie in the plane. So that's our first vector found, and a point that's on the line. Because the line is in the plane, the point is also in the plane. So if I combine my powers here, I can say that I have a point P, which is 0, 0, 1. That one was given to us. And I've got a second point Q, 2, 3, 1, which I got from the equation of the line. So I could find a second vector by connecting those 2 points. So my vector PQ should be 2, 3, 0. All right, I'll take Q and subtract P. 2 minus 0, 3 minus 0, 1 minus 1. And now I can get a cross product of two vectors because I have two of them. So I'm going to call this V cross PQ. V is going to be the vector that I take from my line, that direction vector 3, 2, 1. And PQ is already labeled, so I'll leave that one as is. That's I, J, K, 3, 2, 1, 2, 3, 0. All right, so let's calculate ourselves a cross product. So for the first component, I get 2 times 0 is 0, minus 1 times 3 is 3. Then I've got 1 times 2 minus 3 times 0. And then 3 times 3 minus 2 times 2. 9 minus 4. If I just break down that cross product thusly, I get that thing. And it's probably worth simplifying it to -3 to 5. And again, that'll be my normal vector. So call it n for normal vector. Now that I've got those two pieces together, I just have to combine them in the correct way. And again, you could go over to your formula sheet. I'd already highlighted one of the pieces I wanted. I've got the equation, the one that's highlighted. A times x minus x naught plus b times da 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 da. You can probably get it from there, where the plane is normal to the vector a, b, c. So let's just go combine that in this equation. Again, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And I've got a normal vector, and I've got two options for my point. I'll just stick with p, though, because it's the easier of the two options. 0, 0, 1. So this is -3 times x minus 0 plus 2 times y minus 0 plus 5 times z minus 1 equals 0. And then I suppose I could simplify that, right? -3x plus 2y plus 5z minus 5 equals 0. Or I could move the 5 over to the other side. I've heard it both ways. But yeah, again, the point should just, or the plane should just be made up of the two elements being a normal vector and any point that's on the plane. Dum, 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 dum. Okay. Oh, I didn't use nearly as much space as I thought I was going to in that problem, but that's fine. All right, parameterization. Doesn't that look lovely? So, write a parameterization in the form R of t equals x of t, y of t, z of t for the curve of intersection between the cylinder and the plane. Don't forget to give bounds for t. So this is just our normal stage of, rewrite x, y, and z in terms of a single parameter t. That's all it's asking us to do, but with, a bunch of fancy words to get there. So let's do that. Step number the first, deciding which variation on parameterizations you want to use. Because there are two main ways that we start trying to parameterize curves. One is to try to pick either x, y, or z to be equal to t, and see if I can express the other two variables in terms of that first variable. So that's like a direct parameterization. Pick one variable, let it be t, see if that works. The other option is to pick two of our variables, x and y usually, and let them be equal to sine of t and cosine of t. And it just kind of depends on the shapes that we're working with. We do that direct parameterization if we have rectangular shapes, or maybe triangular shapes, polygonal shapes, really, polygonal shapes. I've heard it both ways. Whereas we do sine and cosine if we have circular shapes. So if we see the equation of a circle show up somewhere, we probably want to be thinking about sine and cosine. And over here, on that spot right there, where I see that x squared plus y squared is equal to a constant number. I see x and y. X squared plus y squared equals to a constant number. That's my main indication that sine and cosine is going to be the better option for the parameterization. So I will start by parameterizing that circle equation. I guess really it's a cylinder because we're in three space now, but cylinders look like two-dimensional shapes because there's a variable missing. But, right, so that's x squared plus y squared equals 9. Then I'm going to use x equals 3 cosine t and y equals 3 sine t. That'll be my first step. Once I've got those two variables figured out, my hope is that I can just direct substitute them into the other equation. So 2x plus 3y plus z becomes 2 times 3 cosine t plus 3 times 3 sine t plus z equals 0, where I'm substituting those two things there and there. And a quick rearranging of the third equation to have z equals should give our parameterization. So r of t is going to be 3 cosine t, 3 sine t, and then this looks like negative 6 cosine t minus 9 sine t. Since if I solve that equation for z, I would just move both of those terms to the other side, which is why both the 6 and the 9 become negative. And also 2 times 3 is 6, 3 times 3 is 9, but I bet you got that part. Quick note on this problem. If I instead had something like x squared plus y squared equals 9z, instead of just equal to 9, I would probably try a different parameterization. If I've got 9z instead of just 9, usually the sine and cosine doesn't work as well there. Oh, right, we're missing a part since I went back up to talk about stuff. Don't forget your bounds on t, because that's an important part of our parameterization. We should say that t is in between 0 and 2 pi, because that's our default choice for t. If we go to a circular parameterization, t should be a full circle, so 0 to 2 pi. Whereas usually if we do a direct parameterization, we usually set it up so that t will exist between 0 and 1. It's like our default choice if we're doing something direct. So we can do line segments from one point to another point. But don't forget that both cylindrical and spherical coordinates are examples of parameterizations. So oftentimes we can use those coordinate systems as models for parameterizations. If we're trying to parameterize a sphere or some part of a sphere, spherical coordinates is a really good model to go to. We might be fixing one of our variables to be like one number, but we can do that because, again, spherical coordinates it's a good model for spheres. If we're doing cylinders, then often cylindrical coordinates is a good model. Just basically what we did here. This is effectively cylindrical coordinates, just with a few of our variables fixed. Speaking of cylindrical coordinates, we've got an equation, r equals tangent theta, secant theta. We want to know what kind of surface it is. No, so r, not r of t. R equals tan theta, secant theta. And now a quick word on the format of the real final exam. I think it's very similar to the format of all of the other exams we've taken, where we wrote pretty much exclusively free response questions. Right? Every question we've seen so far was a free response question. We haven't had any multiple choice or true false. And when we wrote the first draft of the final exam, it was the same way. Every single question was free response. Then we looked at one that was similar to this, where we are asked you to identify a surface, and decided that that free response question was better if it had a word box or an answer box. So this isn't exactly a multiple choice question, but it kind of is, right? So this is the most multiple choice we'll get on the final exam, where maybe we'll ask you to identify a surface. And if we do ask you to identify a surface, we'll provide all of the available options. So I don't know, does that count as adding a multiple choice question? Technically, yeah, but I think in spirit, it wasn't supposed to be. So technically, you might see a multiple choice question on the final, or maybe we just cut this problem. You don't know. I know though. So if a question like this showed up, again, it'll have the answer box there to choose from the options. No more than this one type of multiple choice question, though. Everything else, expect the usual free response set. All right, again, I'll hop off that soapbox and come back to solving this problem. All right, tangent theta. So what I'm doing here is noticing that I've got a secant theta on the right side. And so I'm going to multiply that secant theta over to the other side, since secant is 1 over cosine. So r equals tangent theta. Secant theta is the same as r cosine theta equals tangent theta. And then these two pieces have particularly nice substitutions from polar coordinates. In fact, if we look over there, we have these two, x equals r cosine theta and y over x equals tangent theta. So I am going to substitute both of those. X equals y over x. Y over x. And then that thing is equal to x squared equals y. That thing is congruent to x squared equals y. Which looks like the equation of a parabola. So that's parabolic. So of my options up above, I'm going to start thinking about parabolic shapes, of which I see only two. I see a parabolic cylinder and I see a paraboloid. Because I've got a parabolic equation, again, I really think it should be one of those, right? Because this is not hyperbolic or circular. And definitely not a plane, since I've got non-linear terms, right? I've got something other than just powers of one on my variables. So from that equation, I again think this thing is parabolic, but also I only see two of my three variables. Only two out of three variables. Right? I don't see a z anywhere in my equation. So if I can express my surface with only two of the three variables, that means I've got a cylinder. Because this shape does not change at all in the z direction. And I can also see that from the beginning, because my original equation had nothing to do with z, even though it was in cylindrical coordinates. It's in cylindrical coordinates, but I only used the parameters r and theta. So I probably could have guessed from the beginning that this thing was cylindrical. And from actually solving the trig equation, I got that it was parabolic. So, parabolic cylinder. Also notice that all of the options that are there, of the 9 options present, those were all surfaces that we looked at in that quadratic surfaces section back in 12.6. sort of right near the end of the exam one material. That's where the word bank got pulled from, was that set. Oh, I guess counting planes. Planes aren't technically quadratic, because they're linear. But still, it's an option. We had to fill the word bank with something. So, yeah, parabolic cylinder. All right, next up, another plane question. This time we want the tangent plane for the surface x squared plus y squared minus z squared equals 1 at the point 1, 2, 2. So let me just scroll, man. Let's just check our formula sheet real quick, see if it's got anything for us. And I don't see anything specific for a tangent plane. I just have back the same stuff about finding planes itself. But that's fine. We can generate our equation for a tangent plane some way, somehow. We just know we need it to fit the equation for a plane. Which means we need to find a normal vector and a point. Just like last time, we already have a point. So we're all out of normal vector. We gotta find normal vector. So couple of options. One is you could remember the formula from the tangent plane section out of the textbook, which is something like z equals z naught plus partial x times x minus x naught plus partial y times y minus y naught. That'll work just fine if you've got an explicit function, which we could force this thing into being an explicit function if we wanted to. Alternatively, what I think is the better option, though admittedly slightly more conceptual. The function f of x, y, and z is equal to x squared plus y squared minus z squared equals 0. Nope. Minus 1 equals 0. There we go. I'm going to write my function so that it is something equal to 0. This will also work if it's a function equal to a constant, so I kind of already had that, but I just kind of wanted to rewrite it so that it's equal to 0, because if I can write my function that way, I know that I can find a normal vector to my surface by taking the gradient of the function. So that's what I'm going to do. Gradient of f is 2x, 2y, negative 2z. And then I know the point I want to be tangent to. So I'll find the gradients at the point 1, 2, 2, which is going to be 2, 4, negative 4. And that is a normal vector to the surface. In particular, this is the normal vector that points down, or this is a normal vector that points down because it's not a unit vector or anything like that. So it's not like one of the only two options. There are a lot of options for normal vectors. This is just one of them. But we know it's connected to the point 1, 2, 2. So that part's good. And we don't really need this normal vector to have a particular orientation because we didn't care about orientation when we were looking at tangent planes. All that orientation stuff came in later. So this normal vector will do us just fine. So all we have to do now is put that normal vector into the equation of a plane, which looks kind of like this. Normal vector dotted with x minus x naught equals 0. Just another equation for a plane. That thing expands out to the usual plane equation. So 2 times x minus 1 plus 4 times y minus 2 minus 4 times z minus 2 equals 0. It's that first equation I wrote down, n dot x hat minus x naught hat. That's just a condensed form for the plane equation. If you expand it out, you get the usual a times x minus x naught plus b times da 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 da. So you don't really need to remember that because again, you have the equation of a plane on the formula sheet. But we do want to simplify this. So I'm going to multiply all these numbers through, and also I'm just going to divide everything by 2 because there's a common factor of 2 all the way through. So this will be x minus 1 plus 2y minus 4 minus 2z plus 4 equals 0. And then I could simplify that part too. Stop that. X plus 2y minus 2z minus 1 equals 0. Yeah, I think that's what we get. Yeah, again, I think that's a perfectly valid way of getting ourselves to an answer. Uh, the other option would be, again, remembering the formula that we had back from this section of the textbook, which will work as well. You'll have a little bit more work to do, though, because you'll have to find an explicit function first, which means taking the square root to get to z, selecting the correct plus or minus option when you do. Though the correct option will be the positive one because z is equal to positive 2 at this point. So we'll need positive 2 for that. And then taking partial derivatives, which involves taking the derivative of a complicated square root function. But it'll all still work out. You can go with that equation if you want. But again, since we have that gradient function and we know that the gradient will give us a tangent, or the gradient will give us a normal vector, I think this is just an easier option, particularly since our surface was not explicit this time. All right, and it looks like we might actually finish this part on time. So, as far as like main concepts that we've looked at, done tangent planes today, done regular planes today. We looked at parameterizations and we looked at surfaces. The main topic that we haven't done yet is maximums and minimums. And that was a pretty big topic from the first half of the semester. So I think that you can also expect to see that guy show up. So, what do we want to do? Find all the critical points of the function, this guy, and classify each critical point as either a local max, a local min, or a saddle point. So there are two main types of questions we asked back in minimums and maximums. One of them was the question we see before us. Find the critical points, classify them as local max or local mins or saddle points. The other option was finding absolute maximums and minimums. In order to have an absolute maximum or minimum, we have to work with a closed region, meaning we'll set some boundary and say that, like, all right, our set's closed. All possible points need to be within this closed set or closed region or closed whatever thing that's there. Meaning we'd have a boundary to parameterize and then look at critical points there as well. But then we don't need to test all of the points. We just plug them in and find the biggest one and the smallest one. So I think you could see either of those two options on the final. And on the original exam too, we asked you the second method, the closed region method, finding absolute maximums and minimums. So we've already tested you on that. And on the practice final, we're asking you to classify those things. So maybe you have a better idea of what to be prepared for on Monday. It's this one. So let's find these critical points. Again, continuing with some concepts. We know that The surface that we have right here, this function, should have critical points wherever its gradient is equal to 0. Yeah, we know that. Yep, its gradient should be 0 at the critical points. It's basically like back in Calc 1 where we said that the derivative of the function should be 0 in order to find critical points. Same thing applies in Calc 3. It's just the gradient now. So that should look like the x partial derivative, which is 2x minus 1, comma the y derivative, which is 1/3 times 3y squared, minus 3/2 times 2y plus 2. And that's equal to the 0 vector, so 0, 0. What's that? It would be just x. Yep. Yeah, good catch. I am not very good with numbers, it turns out. Yeah, just x minus 1, not 2x minus 1. Yeah, I took my time with the y partial and then I don't know. Just skipped some steps with x. But anyway, that gives me the two equations. X minus 1 equals 0 and y squared minus 3y plus 2 equals 0. You might also remember this as just f partial x equals that and f partial y equals that, which is also a totally valid way to have started the problem. Just find f partial x, find f partial y, set them both equal to 0. It's the same thing as finding the gradient and setting it equal to 0. Right? Those two options should be the same. Solving this system of equations, I get x equals 1, and I need to factor the other side. Though if you wanted, you could just look at that quadratic equation and jump straight to an answer. I wouldn't be too surprised. But in case it's been a minute, y equals 1 or y equals 2 after I factor that thing. If you completely blank on factoring, don't forget that the quadratic formula could work here as well. It's a little bit more cumbersome, but still works. So that gives me 2 critical points. Critical points. Because remember, we have to solve this system, which means both equations have to be true at the same time. So I've got the point 1, 1, and I've got the point 1, 2. This one was a fairly straightforward system to solve. I did not need to substitute from one equation into another, which was mighty kind. Because often that can be a bit of a headache. But yeah, x has to be 1 at critical points, and then y has two options, either 1 or 2. So next up, we've got to classify these 2 critical points. And we've got 3 options: local minimum, local maximum, or a saddle point. We could also, yeah, we'll just stick with those 3. Neither won't particularly be an option, though it is possible for the test we're about to use to fail. But speaking of that test, let's go back up to the formula sheet. Pretty sure I highlighted it because I knew we'd be coming back to it. Yeah. This bit right here for the second derivative test. First, we need to make sure that the first order partial derivatives, being partial x and partial y, are both equal to 0. Then we define this d guy, which is sort of like a determinant, where it's the 2 straight second order partial derivatives minus the mixed second order partial derivative squared. And that thing will tell us something. If that number is positive, we have either a local maximum or a minimum. Pin on that for a second. If that determinant number is negative, we have a saddle point. Because if that determinant number is negative, that means the mixed partials are more important, or just it actually doesn't mean that. If that number is negative, it means that the straight second order partial derivatives have opposite signs. That's basically the only way for that to happen. So that means that like x is concave up, but y is concave down. Since they don't agree with each other, that thing makes a saddle point. But back to the option where the determinant thing, is positive. If d is greater than 0, then that means that the two straight second order partial derivatives must agree with each other. They must have the same sign. They're either both positive or they're both negative. The only way for d itself to come out positive. So remember that second derivatives tell us concavity. So if both of those derivatives are positive, somewhat counterintuitively, I have a local minimum. Because that means the thing is concave up, and a concave up shape is going to have a minimum down at the bottom of it. Conversely, if both of those second derivatives are negative, meaning my graph is concave down in both directions, I'll have a local maximum. Because it's concave down, so I've got a local maximum at the top of that shape. So that's our test. So we should just go calculate a couple of things. So let me put that stuff back on screen. I need the straight second order derivatives. Partial x is just 1. Partial y is 2y minus 3. And the mixed second order partial derivative, partial x, partial y, or partial y, partial x, remember that those should be the same as long as we have a nice function, is 0 from either case. Since neither of the first order derivatives depended on the other variable. Each of our terms were independent. So that means the value we want to be checking, we call d, looks like 1 times 2y minus 3 minus 0 squared, which is just 2y minus 3. So I want to look at d of 1, 1, and I want to look at d of 1, 2. So if I plug in 1, 1, I'll get 2 minus 3, which is negative 1. So that tells me that 1, 1 is a saddle point. So they slide me a little bit that way, condense me just a little bit. That number is less than 0, which is what tells me that I have a saddle point over here. Next up, I've got 1, 2, which is equal to 2 minus 3, which is positive 1. And that number is greater than 0. Next, I'll come back to that in a minute. And I also see that the straight second order partial derivative f partial x is also greater than 0. Which means that the x direction is concave up. And also, f partial y is greater than 0 because it's equal to 1. Right? I don't need to check both of them. I just need to check either of them because if d is positive, I know that they'll both have the same sign. So since d is positive and partial x was positive, I know that partial y will be positive as well. But again, second derivatives tell us concavity. So this guy is concave up. So with both of our powers combined, I know that 1, 2 is either a local minimum or a local maximum, just based on the fact that D was positive. But because it is concave up, this thing is a local minimum. And let's put that in blue too. Right, concave up again should be local minimum. I talked about that when we looked at the test. And wouldn't you know it, managed to finish on time. Cool. So I will stop things here. Okay, bye, 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 bye.